Good day to each and everyone. I am Reginald Tejana of Grade 12 STEM Boyle. On this date, I will be going to be your reporter 33. So, let's start. So, we're going to tackle about apply Newton's first law to obtain quantitative and qualitative conclusions about the contact and non-contact forces acting on a body in equilibrium. So, what is Newton's first law of motion? Newton's first law of motion, also called as a law of inertia, states that a body at rest continues to remain at rest and a body in constant velocity continues to be in a constant uniform motion unless acted upon by an unbalanced force. This law highlights the concept of inertia, which is the tendency of an object to resist changes in its motion. In simpler terms, objects will stay still or keep moving in a straight line unless something pushes or pulls them in a different direction. When a body is in equilibrium, the net external force acting on it is zero. This means that the force acting on a body must be balanced with the contact and non-contact forces cancelling each other out. So, what is contact forces? Contact forces are those that results from direct physical contact between objects such as tension, normal force, kinetic and static friction, and fluid resistance, while non-contact forces, on the other hand, act at a distance such as gravitational and electromagnetic forces. So imagine you're standing still on the ground, not moving an inch. This is a perfect example of equilibrium. What's happening in this moment is that the forces acting on your body are all balanced out. The force of gravity pulling you downwards is perfectly countered by the normal force exerted by the ground pushing you upwards. These two forces, which is contact and non-contact forces, one pulling you up, down, and one pushing you up, cancel each other out, resulting in zero net external force acting on you. So Newton's first law tells that when a body is acted on by zero net force, it moves with constant velocity and zero acceleration. But when the net force is not zero, the inertial properties of a body are characterized by its mass. If no force is applied, its motion remains unchanged. When there is an unbalanced force, the object's mass determines how much it will accelerate. Mass measures an object's resistance to changes in motion, so heavier objects require more force to accelerate compared to lighter ones. It is important to note that the net force is what matters in Newton's first law, so zero net force is equivalent to no force at all. The law of inertia, or Newton's first law of motion, considers only equilibrium of a body that can be modeled as a particle. For a body to be in equilibrium, it must be acted on by no force, or by several forces, such that their net force is zero. This means that when an object is at rest or moving with constant velocity in an inertial frame of reference, the net force on it, which is the vector sum of all forces acting on it, must be zero. This law implies that there is no fundamental difference between bodies at rest and one that is in constant as long as no external forces act on them. Whether stationary or moving at a steady speed, an object will maintain its state due to inertia, and motion is related to the observer's frame of reference. So the greater the mass of an object, the greater its inertia, and the smaller the mass of an object, the less its inertia. So let's move on to quantitative analysis. To quantitatively analyze a body in equilibrium, we use vector addition. The sum of all forces in each direction, horizontal and vertical, must equal to 0. For vertical versus, sum of the forces in the y direction equals 0. For example, for a book on a table, if the book's weight W is 10 newtons downward, then the normal force N must be 10 newtons upward to keep the book in equilibrium. Horizontal forces, sum of the forces in the x direction equals 0. For example, if a box is pulled by a force of 15 newtons to the right and friction acts with a force of 15 newtons to the left, the box remains stationary. Qualitative analysis. In equilibrium, qualitative insights include balance forces. The forces must counteract each other perfectly. No unbalanced force means no acceleration or change in velocity. Number 2, internal versus external forces. Internal forces like tension in a rope are balanced by other forces within the system, while external forces must be balanced with respect to the environment. So here are the examples. In static equilibrium example, a book resting on a table, like in kanina. The forces are gravitational force downward and normal force upward. Both forces are equal in magnitude but opposite in direction, keeping the book in static equilibrium. Next, in dynamic equilibrium, a car traveling at a constant speed on a highway. The forces are driving force forward and frictional force backward. Both forces are equal, resulting in no acceleration and maintaining a constant velocity. So, Newton's law of inertia as well as Republic Act 8750, otherwise known as the Seatbelt Use Act of 1999, are the two reasons why we should use seatbelts. A person inside the car moves with the same velocity as the car. If the car collides with a hard object, the net force acting on the car causes it to stop. The passenger will continue to move at this velocity unless a force stops him. This force is provided by the seat belt. When worn properly, the seat belt helps spread the stopping force to bigger and sturdier parts of the body, the rib cage and the pelvis, to minimize damage. In conclusion, applying Newton's first law to analyze contact and non-contact forces on a body in equilibrium allows us to gain a deeper understanding of the forces at play and how they interact to keep the body stationary. This knowledge can be applied to problem-solving scenarios in single-body and multi-body dynamics, as well as on experiments involving forces. By using Newton's laws of motion and relevant concepts such as action-reaction pairs and inertial reference frames, we can effectively analyze and manipulate forces to achieve desired outcomes.